Okay, so actually, what I'm going to be talking about as Filippo leaves, you're still here? Okay, good. Because I'm going to be asking exactly the same question that Filippo was asking about whether or not humans search like animals, but from a psychologist's perspective. So trying to look at the mechanisms that people are using and how that compares with the mechanisms that we think animals are using to make their decisions about searching through different kinds of environments. So people and other animals have to look for lots of different kinds of resources to survive and to reproduce, including things like food, social partners, information about their environment. Lots of these resources we could characterize as being structured as networks and then talk about how the individual is searching through a network. I'm going to be focusing without that particular emphasis, but we can talk about that if you want to in questions. And one of the differences from what Filippo is talking about is that the environments I'm going to focus on are environments where the resources often come in patches, that is, locally dense collections of resources. So you can think of patches of berries, like a berry bush full of different delicious raspberries that you can pick and eat or collect until at some point you run out of those berries. There aren't enough ripe ones left there to find easily enough that you decide, okay, it's time to leave this patch and go off and look for another patch that might be over the next ridge. So when resources are distributed in patches in this way, then it's not just a question of exploring, like Filippo was talking about exploring in bid space, but also exploiting patches. So once you find a resource, there's probably other resources near it, a whole patch of them, and you have to decide how long am I going to stay and exploit this patch of resources before I decide to leave and go explore for a new set of resources. So individuals in these kinds of environments, which are very common, have to make this exploration-exploitation trade-off. In a little more detail, what animals we can think about their search in space have to do is, first of all, find a resource patch, assuming that the resources are patchy. That's the exploration process. Then they have to stay in that patch once they've found it for as long as that patch is producing enough resources for them to make it worth their while, and that can be formalized. And that is exploiting that patch. And then they have to decide, once they have depleted that patch, when it's time to leave that patch and start exploring for a new patch. And so that is switching from exploiting back to exploring. And what we want to know is how humans are making those decisions in various different kinds of environments. And that could be spatial environments, like for food. It can be informational environments, as I'll be showing you. One of the first studies that we did to look at this question was a kind of spatial task in which subjects came into the lab and had to assume the role of being fisher people. And they were confronted with a sequence of ponds that had fish in them. They saw these on a computer screen. Fish would rise to the surface and they would catch these fish. They didn't know how many fish were in each of the ponds that they went to, and the more fish they caught, the fewer there were left in the pond, and the longer it took between fish for the next fish to come. They could never tell, is this pond completely empty or there might still be fish in there? Should I keep waiting or should I decide to leave? So they had to make this decision, continue exploiting or leave this pond by pressing the big red next pond button and then be taken to a new pond where they could exploit again. So they didn't have to explore. Here they just had to exploit and decide when to stop exploiting and be taken to automatically to a new resource. The data from this kind of a study can be visualized in this way. These are plots for individual people. Here's one subject's data blown up, and we have how long they've been on the patch on the x-axis, how many things they have found on the patch, in this case fish, on the y-axis. Each of these blue lines is their path through time at one pond. So they didn't find anything for a while, then they caught a fish, didn't find one for a while, caught another fish, another one appeared soon, no fish for a while, then they caught one, etc. Up until where these black asterisks are, those are the times at which they decide to switch and get taken to a new pond. And so what we want to explain is what is the pattern of those leaving decisions, these black stars. Overall, in this kind of a search experiment, the more resources that people are finding, the longer they stay in a patch, which is a reasonable and near optimal kind of approach that fits with some predictions from optimal foraging theory that have been developed for animal decision making. They're using a simple giving up time heuristic, which is after they haven't found a fish for some threshold of time, they decide it's time to leave this patch, take me to a new one. We found in a similar kind of study, but where we gave people a Scrabble task where they had to look for words in a collection, random collection of letters, that people made the same kinds of patch leaving decisions. But we also wanted to look at whether or not people searched internally in their own memory in a way that corresponded to this kind of patchy foraging strategy. And so in this case, what we wanted to see, again, was were they following these predictions from optimal foraging theory? The marginal value theorem is a specific theorem that says when you should leave a patch in this kind of situation. What we did was we gave them a task to search their memories for particular concepts. For instance, name all the animals that you can come up with in 3 minutes. Okay, just go. What happens when you ask people to do this is that they usually produce things in clusters or patches. I'll show you this in just a second. And they leave those patches and look for new ones. And we got a bunch of data from undergrads here and looked at what were their patterns of deciding when to leave these patches in memory. What it looks like is everybody basically first says dog, which probably is what you all came up with in your head, and of course the next word is cat. And then you might think of some other pets, perhaps guinea pig, hamster, or ferret if you had one of those. And then you might kind of run out of pets to name. And then think of, okay, what other kind of animals can I think of? Oh, goats, chickens, pigs, horses, cows, so farm animals. And then run out of those over time, wait for a second to think of another kind of animal and come up with sea animals, and then start exploiting that patch. So this is how the data looks when people are doing this kind of a task. When we are observing what they're doing, when there are these long transitions between items that people are producing, that's indicative of them switching from one patch to another. And when people decide to switch, again, is predicted by optimal foraging theory, by that marginal value theorem. They basically switch at the point at which it would be better to switch and go find a new patch than to try to keep on exploiting the current patch that they're not having as much luck in. So people are doing a good job at making this exploration-exploitation trade-off. This is similar to what's also been found in web search work that Peter Paroli and Stu Card have done in previous years, looking at how long do people stay in web page patches on the web before they decide, okay, I'm not finding enough good stuff here, time to go find a new patch. That's a lot of words. So people are searching in memory, in their semantic memory, through patches, again, as predicted by this marginal value theorem. And that suggests that people are using the same kinds of mechanisms for searching in space as they are for searching in other kinds of domains, in this case, an informational domain internally in memory. But what we don't know from that result yet is what exactly are the mechanisms that people are using to decide when to switch. We just know they're doing, so far, a good job of this. In particular, it could be that people aren't thinking and deciding, okay, I can't find anything more in this patch, it's now time to switch. They might instead just be hopping around in their semantic network and sometimes taking longer hops, exactly like a levee flight. And so in order to try and find out which of those two options seem to best account for people's behavior, we're going to be putting them into the scanner to do this same task with Josh Brown here in psychological and brain sciences. And we'll look for whether or not we see evidence of switching mechanisms that have been found in other kinds of tasks in the scanner are being employed in this kind of a task as well. If we find those, it's support for the exploiting, exploring, switching idea. If we don't find those, then it sounds like people might just be taking hops of different sizes through their semantic network. And that's stuff that Alex is helping us with. There's a lot more work on these topics of cognitive search and how people and animals search in different kinds of spaces in this book. Maybe I should put my slides online. Plug. Here's another couple of examples of different kinds of spaces that we are looking at people's exploration in. One with Jared Lawrence, grad student in our lab, is on how people move around in music space. How do you decide after you've listened to one set of songs or one set of artists what you're going to listen to next? One of the things that we need in order to look at this is some kind of understanding of how music space is structured, and there are different places that structure music or propose different music structures online, like EchoNest has this kind of map of music space based on the similarity between the songs. And what we are doing is looking at how people are moving around in space by looking at listening data from Last.fm. And this is a rather large data set. So this is Scrabbles are individual songs that people have listened to. So far, Jared has scraped 1.2 billion of those from 73,000 people, which for you guys in network science, maybe not a big deal, but in psychology, that's really big data. And so we're looking in that data at how people are moving from artist to artist or from genre to genre. Are they giving up on a patch after they're not getting much more enjoyment out of it, for instance? Another thing that we can look at is how do people create the structure that allows themselves and other people to search through that space? And that structure is in the form of tags. And we've been looking at how people are deciding when to tag different things that they're listening to. Are they tagging things so that they can find them themselves again later? Or are they tagging them to build structure for other people to find that music? Are they saying, hey, if you want to find this really excellent 1970s UK psychedelic song, this is the one that you should go to? Or is it so that when they want to find that one that they like, that they can find it? And one of the ways that we're doing that, which is shown on this graph, is to look at when are people tagging versus when they are listening to songs. And so these green lines are when people are tagging, and the blue lines are when they are listening to songs over time. This is the relative proportion of both of those activities. So we're trying to see, are people tagging things when it looks like they would want to be remembering them in the future, or are they tagging them so that other people can find those things? Another kind of space that we're looking at is food space. How do people decide what to eat over time? This is an illustration of making the decision not to ever decide what to eat over time. This is Soylent, which I know some people on campus are actually using as their main dietary source. Most people choose different things to eat on a day-to-day basis. And what we want to know is how people are deciding what to eat next based on what they've eaten recently. So how people are moving through food space. So we need to have ways of finding out what are the choices that people are making about what to eat over time, which is challenging in itself, and also how are they thinking about the food space, which is also challenging. There's lots of reasons why knowing both of those things could be useful. So we can study how people come to be experts in a domain as they are moving through this space. Can we see traces of how experts choose what things to eat next compared to novices? We can look at health effects, which include how much variety people are eating over time. We can look at differences between individuals in terms of some people explore a lot and some people don't explore very much. And also food waste is something that can be predicted by how people are exploring in this space. If they're trying lots of things that they don't like, they're more likely to be wasting more. So some sources of data on what people are eating over time can be found online. We've worked with a site called Tweet What You Eat, where people are recording the things that they're eating meal after meal. This is useful because people type in or tweeting what they're eating rather than taking photos, so that way we don't have to try to recognize from their weird photos what that casserole was that they were eating. We have them telling us exactly what it was. And so we can get data like this on, now it sort of looks like the bid data, but slightly different form, looking at all the different things that this one individual is eating over time, and we can see how are they moving through cuisine space if we have some way of characterizing where are they in cuisine space and food space each time they're eating those things. So one of the things we can do is look at how often are they repeating the same thing. If they eat a hamburger on day one, how soon is it before they repeat and have a hamburger again? Are they more likely to have one in coming days, or are they less likely to have one in coming days? And this is a graph of lots of different foods on the y-axis against the days that those foods were consumed on the x-axis. And so you can see some things are being eaten in clusters, like there was a bad week when this person ate nougat every single day. Some things get eaten in clusters, some things get spread out over time. And we can look at the likelihood of eating the same thing on the next day if you ate it on the previous day, and that falls off very quickly, presumably a power law. But we also need, again, to characterize how are they moving through cuisine space. And so in order to do that, we have to characterize cuisine space. How best to do that? Well, one way is to make use of what YYON here has been doing in terms of flavor networks, and we're working together on these questions. Do people think that two foods are close to each other if they share a lot of flavor compounds in common? Or do people think that two foods are similar to each other if they have a lot of nutrients in common? Or are they deciding on the basis of the dishes, like their cultural origin or how they are produced, other aspects of potential similarity between foods? That's what we're trying to see. What are the appropriate ways of characterizing this cuisine space that people are moving through over time? Another thing that we want to do is look at individual differences in the amount of exploration versus exploitation and whether those carry for a given individual across different domains. So is somebody who explores a lot in one domain more likely to explore a lot in another domain? Again, with YY, we're looking at this particular question in the Yelp dataset challenge to look at reviewers on Yelp who are reviewing different restaurants. How far are they traveling in space? So to go from restaurant to review these different restaurants, compared to how widely are they exploring cuisine space? Are those people who are more willing to explore widely, drive to other cities to go to restaurants, people who are more explorative and, say, adventurous in cuisine space and they're eating from a bunch of different cuisines as well? Or are those people always just looking for the very best Chinese restaurant and have a very narrow cuisine space that they're trying to explore? One last thing, another way of looking at these individual differences in exploration versus exploitation is to strip away all the real-world complexity and make a lab task that's as pure exploration and exploitation as we can, and then see whether or not behavior on that task correlates to search behavior in different kinds of domains for each individual that we're measuring. And so this is a card search task that another grad student in our lab has been developing, and very simply, the task is, it's a game where you have a certain number of turns to go through cards in a deck, and you can either explore or exploit on each turn, and your goal is to get as many points as you can out of 20 turns or 30 turns, however many we tell people, of this game. So on each turn, you can explore by clicking on this deck, and then a card appears on the screen, and that's how many points you get, however many points appear on that card. And in most of these cases, you know what is the range of values in the deck. So in this case, it's 1 to 100. And so you might think, well, that's not good enough. I want to keep on exploring. And so click on the deck again, get another card. Not good enough. I'm going to explore again. Oh, that's even worse. Explore again. Oh, that's a good value. And now I can switch to exploiting that card and click on this card instead, and 91 points appears in my point total, which is down here, and I want to exploit it again. I get 91 points again, and I can just keep on exploiting that for the rest of my turns. Or I could go back to exploring and saying, maybe I can do better, maybe I can get a higher value. And so we're collecting this data from people to see how much each individual switches between exploring and exploiting in this situation where basically that's all they have to do. And then again, we'll be getting other behavioral measures, for instance, how much they explore in the food domain, how much they explore in the social domain, and see whether or not this kind of task predicts how much people are exploring and exploiting in those other domains as well. So overall, what we're finding is that people are using rather similar, in some cases exactly the same kinds of foraging strategies in different kinds of spaces that we're searching for resources in. Spaces in which, again, the resources are clustered or patchy. And these strategies that people are using match the predictions from optimal foraging theory that were developed to describe how animals are searching for the resources in their environments. And that suggests overall that there are similar deep-level neurological mechanisms that are driven by dopamine, probably, that have evolved from the original search domain, which was food, and now get applied to how people search for resources in all sorts of other domains as well. And I'll leave it there. Take your questions. Thank you.
We have 5 minutes for questions.
So are there heuristics that you understood that can be applied in other domains?
Yes. Right. So these patch-leaving heuristics, a number of them have been described for animals. Things like the giving up time heuristic that I mentioned that we find people using as well in our tasks, which again is if you're looking for resources and you can find them at different points in time, after there's been too long of a delay since the last one that you found, like the last berry that you found or the last fish that you caught, then you leave the patch. So that's one kind of heuristic. Another kind of heuristic is called a fixed time heuristic. So you stay in each patch for a fixed amount of time. It doesn't matter how much stuff you're finding. And then you switch. Others look at a fixed amount of number of items that you have found. Once you've found that fixed number of items, then you switch. And different of these heuristics are appropriate for different kinds of environment structures too, in terms of the distribution of patch sizes. So that fit between the rules and the environment structure has also been well explored.
Also, there is also a taxonomy of different environments based on which heuristic is best.
Yes. Yep. Yep. I don't know.
What I found very interesting is that in those experiments in which you are studying animals, in which you created the patches, I mean, that is in your mind, so presumably you put stuff in those patches, and then now you look at that. Have you ever explored the connection between the patches that you created and are you searching for?
We haven't done that yet, but that's a great question. So what is the nature of the patches that are in there that the people presumably have constructed, but could have constructed based on input from the external world as well? Another aspect is that if you ask people to search through a set of concepts in different ways, then people can also construct patches or categories on the fly too. So there's some trickiness that we have to be careful of there in terms of Are we looking at real patches that exist, independent of what we're asking people to do, or are they creating them on the fly as we're asking them? Yeah, that's a great question. David?
So if I'm right, when you have, you've got some tasks that both people and people are carrying out in the real world, and you have other tasks that they're carrying out in a computer environment.
Right.
And the way you've been talking seems to suggest that you're presuming that the behavior in both environments is the same. Do you have any way to test that? Is there a way to see whether these kinds of strategies that are carried out in computerized environments are different from the way
If we can get enough data observing how people are making the choices in the real world, then we could make more fine-grained comparisons of what they're doing. So you're absolutely right that the comparison between the lab behavior and the real world behavior is a bit limited in what we're able to do so far. In some cases, what we're doing is looking at patterns of real-world behavior and seeing whether they would fit with an assumption that people are using a particular strategy, but that's as far as we can go until we're able to get finer-grained data on like the time between the decisions that people are making, what's the exact structure of the environment that they are facing and making those decisions in. Right.
which means that there may be forms of behavior that follow from the design of the game, or in your case, the design of the experiment, so popcorn effect. I'm cautious about taking those inferences.
Absolutely. So far we have some compelling evidence that things look like they're the same, but we don't have, of course, knockdown evidence that it is exactly the same. But this is a challenge that anybody doing experimental lab psychology research, cognitive science research faces. So it's a common problem. Absolutely. Luis. Right. Yeah. So that's a great question too about what's the nature of the environment. So when people are using Last.fm, in some cases we don't even know where their listens are coming from. They're being recorded, but they might be coming from other services and just being recorded by Last.fm. There are other things that we do know are constraints and that we need to take into account, in particular with the tagging. When we're looking at what tags people come up with, they get suggested a set of tags, or they get told here are the 5 most common tags, for instance, for a given piece of music. And we don't know what those tags are that they're seeing, and so we can't be sure if they are copying one of those or coming up with their own tag. So that's an example of where, again, it would be great if we could get more information. Last.fm has that information, but we haven't been able to get it. Right. Absolutely. But if you really cared, like, I'm sick to death of this patch, it's time to make a choice, we would see that in there, right? Yeah. Alex?
So the optimal foraging theory seems to depend on the structure of the overall space that you're searching within.
Right.
But in some of these informational spaces, that space is changing at the same rate at which you're searching the space. So new songs are coming up instantly all of the time. So it's not like I just exploited a patch. I can never return to that patch again. That's going to be continually renewed. So how does this, would you expect the same theory to hold in those instances, or do you think that you would have to change things around to take into account the changing structure of the global?
So the way I was talking about the patch leaving decision so far were that you're depleting a patch and then it's done and you go off and you find a new patch. And so that depletion, that permanent depletion assumption, of course, can be relaxed and doesn't match lots of real-world situations. The berries on the bush are going to regrow at some point, or the ones that aren't ripe yet are going to get ripe. And so that certainly has been explored, what happens when you have patches that replenish. And so that part of it we could also apply to the music listening, for instance, which replenishes, like you say, in that bands come out with new albums, new songs, some of them, but also that our enjoyment of something that we've been away from over time also replenishes. And so we need to take that into account as well, to look at the rate at which people would return to a given cultural patch, for instance, music. Yeah. So there's some theory already out there that could be used for that. And some of the things are going to have new theories being developed as well.
Hi, I'm Orlando Ross. Bernice has to go to the job search meeting. Thanks to Legal and Peter for a very interesting talk.
Thank you.